In this video, we are going to create scatterplots, and then we're going to calculate covariance and correlation. So first we need to run our startup chunk. Notice we have a couple of different packages that we are loading that are going to allow us to use some special functions to do different things. And then we need to read in the data. We're using the US air pollution data, which is found in an R package. And so I also am outputting the structure of the data just so you can see what this is. So it includes several factors related to air pollution, SO2, temperature, amount of manufacturing that's done, the population of the city, the average wind, average precipitation, days that had precipitation, and then there's a factor variable on the population, and it's either small or big. Okay, and now to create scatterplots. So this is the most basic scatterplot here at the top. We just use the plot function. The first variable that we include will be on the x-axis. The second variable will be on the y-axis. And then these two label options we can include if we want to change the labels that are going to be written for the axes. If we don't include this part, then the variable names will be there. So let's run just this line of code, and then you can see we have a very simple scatterplot that is created. We can also add a regression fit line to this. So LM stands for linear model, and then notice we had to change the order of the variables because what this says is we are predicting precipitation from temperature. So precipitation is the y variable and temperature is the x variable. If you try to run just this second line, you'll get an error. It won't work. R doesn't know what to do. You have to run that at the same time that you create the scatter plot. So if you highlight both of these lines and run it, then it works. And you go back down to your figure, it's the same scatter plot as before, but now we have this line of best fit based on a regression analysis. Okay, we also have lots of other options that we can use to enhance or add different aspects to the scatter plot. And in this case, we're using the scatterplot function from the car package, so that's why we loaded that package in the beginning. And so first let's go ahead and run the command, and then we'll talk about the different options. So if we just run all of this, this was what it looks like. So now we have two different groups. We've created separate data points and separate regression lines depending on whether the population was big or small. And then notice that we've added box plots on both of the axis labels, so that's kind of a cool feature. So how did we do this? Okay, so we use the function scatterplot, and then we are predicting precipitation from temperature. So precipitation is the y variable, temperature is the x variable. And this little line tells R that the variable that comes after it is going to be our grouping variable. So we have this one factor where population was divided into big population or small population. We tell it what our data set name is. Again, we have the labels that we are changing. We can also adjust our legend title to be something other than the variable name. So we're made that population. So, and then here we have set smoother to false. So the smoother, as I noted in the notes, indicates whether to include a smooth line. So the default is to show the line, and if you don't want to show it, you have to put F for false. So that's what we had. If we want to have that line, we can just take out this option. We can just delete it, and then when we run this again, now we have those lines in there. So we have one for each of our categorical variables. So this is the smooth line for the big cities, and then the red is the smooth line for the small cities. I think it's kind of too busy with that line in there, and I actually prefer not to have it. So I'm going to add that back into what we're doing. And then this next option is, this is what allowed us to add the box plots on the axes. You can choose to just do it on the x-axis and then you would just have an x here, or just on the y-axis and then you would only have a y here, Or if you don't want to include them at all, you just take out this option and then they would go away or not be there to begin with. And then jitter, this can be an especially useful option if you have a very large data set and if a lot of your data points are either very close together or even exactly the same. So if you have sort of fewer options of where things can lie, if you have like a 7-point scale and it's just a one item, then everybody has to be on one of those points, and then sometimes it's hard to see what's going on. So jitter kind of moves those points just a little bit off from each other so you can see them better. And so this, I wanted it to jitter for both the x and the y variable. If you only wanted it to do that for one variable, then you can include just x or just y. And in the scatter plot that we have, it doesn't really make much of a difference if you use this option or not, because the data set's pretty small and there aren't a lot of overlapping points. So that's something you might just want to play with, do it with it and do it without it, and see if it makes a difference. And then xlim stands for, or lim stands for limit, so we can set the limits of both of our axes. So here I said to set the x limit for the minimum value to be 40 and the maximum value to be 80. If you wanted to also set the y-axis, you would just use y-lim instead of x-lim. And if you don't put anything here, then it just defaults to what fits best for the data. And then this final option, grid equals false, means we don't get the background grid. So if you want to see what it looks like if we have the background grid, just take that part out, run it without it, and you just get these gray lines in the background. So that might be helpful, or you might think it's distracting. Definitely that's a personal preference as to whether you want to include that or not. Okay, a couple of other options to comment on, but that aren't in what we did down here, is you could also choose to get rid of the regression line. So if you don't even want the straight lines in there, you can just say reg.line equals false and that will go away. You can change the width of that linear regression line. So if you want that to stand out more, you could make the width bigger. So if you wanted to see what that looks like, if we add comma LWD, the default is 1. So we want to see a big difference. Let's maybe make it a 3. It's going to be 3 times as wide as it is now. All right, so now those lines really stand out. You might have a reason for wanting those to stand out. Legend.chords. This can be used to specify where the legend for the grouping variable should be. So notice the default is it's outside of the figure, above the left side of the figure. It's kind of a nice place for it. It doesn't interfere with the figure. But if you were trying to save room or if you wanted to put it somewhere else, you could do that. So again, legend chords is the function, and then you have several options, and those need to be in double quotes. So if we want to see what that looks like, we could add that. So legend.chords, and it even fills in that option for you. So if you just hit return, it will do that. And then let's say we want it top left. So now that puts it within the figure on the top left side. So you can put it in any corner, or you can put it just the top, which is the middle, you can put it right in the center. There's kind of some strange options for where to put it, so you can kind of play with that and see what you like the best. So next we have the option by.groups. By default this is set to true, so this means that we're going to get a regression line per group, which is exactly what we have. We have one regression line for the small cities and a separate regression line for the big cities. If we want just a single regression line, then we have to set this option to false. So we can go add that. So we can do by.groups equals capital F. And then we get a single regression line for both of the groups. And then we already talked about this grid option. So as you can see, there are lots of different things that you can do to customize a scatter plot. Okay, so next we're going to look at doing a scatter plot matrix. So we want to look at how more than just 2 variables look like in a scatter plot. So the command we're going to use is scatterplot and then capital matrix afterwards. This is also in the car package. And now we have multiple variables that we're listing. Notice we start with this little tilde, and then we have plus signs, in between the variables. And so this is the order that the variables will be plotted in. We tell it which data set we want to use, and we tell it where to get the row names from. So let's go ahead and run just this basic one. So this is with all of the defaults. So we just have our variables on the diagonal with a density plot, and then you can see how each of them correlate with the other. So SO2 levels, sulfur dioxide levels, and the number of manufacturing plants are pretty positively correlated, although you've got a lot going on down here and not as much on the higher end. And you can see this is pretty busy. We've got a red line, we've got a green line, we've got red dotted lines, so you may or may not be happy with how much that's showing or what's showing on the diagonal. So again, there are also lots of options for a scatter plot matrix, just like they are for a single scatter plot, and a lot of those are the same. We can also use a grouping variable like we did with the scatter plot above. So we have the same variables in the matrix, and now we're adding this grouping variable of small and big populations. So that just puts the key for that in our upper left-hand diagonal box, and then you can easily identify between the two of those with the black circles or the red triangles, and then also with the colors of the lines for other things. So that can be helpful if you want to look at how two groups might differ in the relationship between multiple variables. And then again, lots of other options that we have, so several that we talked about when we talked about just a single scatter plot. So let's run this so we can see what it looks like. Look at some of our different options. So some of the things we've used. So we changed our variable labels. Instead of just being what the variables are called in the data set, now we have sort of nicer labels, which might be especially good for a presentation or a publication. We can change what shows up on the diagonals. So here we told R that we want a histogram on the diagonals, and you have multiple options so that density distribution is the default. If you want that, you don't have to include that option. That's just what you'll get. But you can also get a box plot, a histogram, which is what we have, a QQ plot, which we'll talk about a little bit later in the semester, but helps you determine if things are normally distributed or not. And then none is you won't get any. So if you want to see what those different options look like, we can just change it here. So if we type in box plot, we'll get box plots on the diagonals, and notice we get one for our grouping variable. So if we didn't have our grouping variable in here, we would have a single box plot in each of the diagonals, but with the grouping variable, we get one for each group. And then if you want to see what the QQ plot looks like, run it with that. So a QQ plot actually is very helpful for normality, like I said. So here you can see that we have some definite outliers on the higher end. So things on the line, that's where we want. Here we have some precipitation outliers on the lower end. Temperature actually looks pretty well distributed. And then if you don't want anything on the diagonals, you just put none as your option, and then you just get nothing. So it's kind of nice. You have this space anyway. You may as well put more information in there. That's kind of how I think about it. So maybe let's go back to the box plots, which is another way you can also see outliers. So beside that QQ plot, right, we can see here we have a couple of outliers for manufacturing, again with precipitation, a couple of outliers on that low end. And then we have n class equals 6. So if we have the histogram, and we use n class, then that sets the number of bars that are going to be within the histogram. If you leave this option out, then it just picks for itself what it wants that number to be. Smoother equals F, it's just like before, so that's why we don't have the smooth lines in there. By.groups equals true, that's how we have separate lines for the different levels of our grouping variable. And then we set the width of that line to 2. Remember, the option is 1, so this is double what the default would be. All right, so once we've looked at our data, then we can actually get to calculating covariance and correlation. So if you just want to look at a covariance and a correlation for two variables, it's pretty simple. So COV and then the name of the two variables in parentheses. If we run just that, it just returns the covariance. So that's the value for the covariance. That's all you get. If you use core, you could also change COV to COR and then it'll output just the correlation. But if you just add .test, then you get extra very useful information. So why not just do it that way? You get a t-value. If you were to convert your R to a t, it gives you the degrees of freedom, and then it gives you a p-value. It also gives you the 95% confidence interval, which of course is helpful. And then this is your point estimate. So if we were to run just core instead of core.test, all we would get is that point estimate. All we get is 0.39, nothing else. So that .test is very useful. Okay, and now we can calculate covariance and correlation for all variables in a data frame or a matrix. And in order to do this, our variables have to be numeric. So the first thing that we did here was we got rid of that last variable that was a factor. So this, remember when we did subsetting earlier, if you use the name of your data set and then in brackets a negative sign in front of the number of that variable, then that variable will be excluded when you create a new data frame. And the way that I knew it was variable 8 was that I used the names function. So names my data and then found out that this pop SB was the 8th variable. So that's how I knew which number to use. And so then when we run this, and now we have mydata.num, now we won't have that variable. So if we look at mydata.num, that last one is gone, and we're left with only numeric variables. So now these functions down here will work. COV and then the name of the data set will give you covariances. This use option tells R what to do with missing data. So this pairwise.complete will delete observations pairwise. So if any pair is missing a value, then that will be excluded. Other options are all.obs if you don't have any missing data, or complete.obs, which will be a list-wise deletion. So across our 4 variables, if any of those variables is missing data, then that person won't be included within the calculation. And then the method option, which you see here with the correlation, allows you to tell R which type of correlation you want. So the default is Pearson. So if you want a Pearson correlation, you can actually just not include this option. But I put it here so you can see what it would look like if you were to add it. And if you want to do a different kind of correlation, you can do a Spearman correlation or a Kendall. Those are your other 2 options. So first let's run the covariance and see what this looks like. So it will give us each variable crossed with all of the other variables. So these are all the covariances. And then we can do the same thing and get correlations. So the layout is the same, but we have correlations instead of covariances. So what if you don't want to correlate all of your variables with all of the other variables? If you only want to correlate some of your variables, a subset of variables with another subset of variables, you can also do that by creating some smaller data sets, basically. So here we're going to create an object called X, where it's going to have from my data just your first and the second variable. And then we're going to create a second object called Y that's going to have variables 3 through 7. So first let's do that. And if you want to see what those look like, you can click on X, right? It's got just those first 2 variables. And you click on Y, and it has the 3rd through the 7th variable. And now we can say we want covariance for X and Y because we've created these 2 new objects. And so now we have SO2 and temperature, that was variables 1 and 2, and the covariance for those with these other variables that were in Y. And then the same thing we can do for correlations. So this is nice if you have a large data set and you want multiple covariances or correlations, but you don't want everything with everything else, which can be a little bit overwhelming if you have a lot of variables. Okay, and now we're going to calculate correlation and covariance for different levels of a categorical variable. This uses a function from the plier package, which we already loaded above. So we start with the function ddply, we tell it the data set we want. This is the grouping variable that we're going to use, so we're going to get separate covariances or correlations for the different levels of this variable. We need it to summarize something. And then we want to use a covariance, and we want that to be equal to the covariance between, and now we're going back just to temperature and precipitation. So if we run that line, it gives us the output up here. So for each level of the population variable, we get the covariance for big cities and also the covariance for small cities. Kind of interesting, look how much stronger the covariance is for small than big. And then we can do the same thing for correlation. We just replace covariance with CORR, and we'll get the correlation instead. And make sure you also change this here. So now we see the correlation, and as it's consistent, that's the smaller cities are actually, the correlation is much stronger than in the big cities. It's kind of interesting. So notice that here what we have in parentheses is actually what it's calling that column for us. How it knows whether to calculate a covariance or a correlation is by the function we put over here. So make sure your label matches your function so you're not confused when you look at your output. Because it would let you do this, right? It would let you say covariance and then calculate a correlation. So if all you did was keep this, that would be very confusing. So make sure that those match. Okay, and then we can also compare correlations with some functions in R that are in the psych package. So first we can look at independent correlations. And so the function is paired.r, and then you have to give it the values. So these are the values of the two correlations we're comparing, 0.52 and 0.12. Null is needed because the same function is used to compare dependent correlations when you have a third correlation to go there. So putting null here really is what tells this function that these are independent correlations instead of dependent correlations. This number is your sample size, and you have to have that there. And then N2 equals is optional and is only needed if your samples have different sample sizes. So if both of your samples were from 60 people, then you could stop here and you'd be fine. But if you have one sample that's 60 and one sample that's 50, then you need to tell R that there's a difference, so it uses the correct degrees of freedom when it's doing things. So if we run this, here's our output. So it just kind of repeats back to us what happened. So it uses X and Y to stand for the different variables, or there is no correlation between variables Y and Z. And then your two sample sizes, it tells you this is a test of the difference between two independent correlations. Make sure it did what you wanted it to do, and it gives you a z-score and then your p-value. So this would be the same z-score that we calculated when we used that equation in class. And then we can also compare dependent correlations with this same function. So these are the first two correlations are the ones that we're comparing. So in this case we have a 0.20 and a 0.45. And then our third correlation, it's not null anymore. Now this is the correlation between the other two variables and then the sample size. And we're only going to have one sample size because that's how it works with dependent correlations. These can't be based on different samples, so we don't have to even worry about this option N2. So let's run that. And the output looks very similar in terms of how it tells you what it did. Now it's a test of the difference between two correlated correlations, so it calls them correlated correlations instead of dependent, but that's the same thing. And then remember, this was a t-value when we calculated it by hand, and again the p-value that goes with it. So here we're seeing that these correlations are significantly different, right? That p is less than 0.05. Okay, and then this last little piece is doing some conversion of correlations. So we can very easily convert to a Fisher Z. So Fisher Z, and then in parentheses is just whatever our correlational value is. We'll return the Z transformed of that. If we want to go back to R, we use Fisher Z to R. So this is sort of an approximation, 0.576, so we should get pretty close back to 0.52 when we go back the other direction, 0.5197. So if you were rounding that off, you'd be back at your 0.52. And then it's also very simple to convert your R effect size to a D effect size, which we haven't talked about much yet. We will pretty soon, but I just thought it would be useful to show you now that you can actually convert very easily from one effect size to another. So an R of 0.52 is the same as a D effect size of 1.22.